So hello, thanks for coming. My name is Warski. I come from Warsaw, Poland. I work for Software Mill, and I would like today to make a comparison between free monads and Tagless Final. Both are approaches to solving more or less the same problem. But before we actually dive into the actual comparison, I would like to motivate a bit why would you want to do it in the first place, because these are tools that solve a specific problem that you might or might not have, or maybe you don't know that you have that problem yet. So we will try to have some like motivation. Why would we want to introduce a solution like free monads or Tagless Final, and then we will see on code examples how some simple examples of these approaches look like. So if you would have any questions throughout the talk, please ask, especially that it will be code. If something is not clear, it will be possible to explain on the fly. OK, so that's probably too small because the resolution changed. So is that big enough? Can you see it on the back? Yeah? OK, good. So here we have like a fairly typical Scala code that we'll be working with. So for now, it's future-based, right? So I guess it's quite like state-of-the-art in Scala. Would you like write business applications? You often use futures in your code. So we have an interface to a database, right? We have a user repository with two methods, find user and update user. They return options, so we kind of suspect, based on the signatures, that there's some asynchronicity going on in the background, right? We somehow suspect that when we invoke these operations, there are some side effects that go to the database, and actually, maybe it's a thread pool that runs synchronous operations, or maybe it's full asynchronous. We don't know that, but we suspect that there's some side effects going on. So that's the user repository interface, and then so the defined user returns an option of user, right? Because the user might not be there. The user, it's a very simple case class. It has 3 fields: ID, email, and the number of loyalty points that the user has gathered throughout his life. So yeah, we have these basic building blocks, and now we have a very simple business method which adds points to a user, right? So maybe let's add a break here so that it's clear. So our class loyalty points, it has access to the user repository through a specific implementation. So we won't be really running any code. We will be only compiling code because in Scala, once you compile the code, it's usually half of your job done or even more, right? And that's good because we want the compiler to actually make as much verification for us as possible so that we don't have to write all those tests. So we will be only compiling code. If it compiles, that's fine. So we won't really see any specific implementation of the user repository, but I guess you kind of suspect what it might do. OK, so we have this loyalty points class over here, and it has an add points method, right? The add points method takes a user ID, the number of points to add, and it returns an either, right? Either meaning either the adding failed, and that's a left, or the adding succeeds, and that's a right of unit, right? The implementation is kind of simple. We find a user in our repository. If there's no user, we return an error, right? Because the user is not found. We cannot add the points. If there is a user, we create a copy of that user with these loyalty points added, and we update the database, right? Because it's all future-based, so we have to use flat map here, right? After finding the user, that's a future, right? The find user returns a future, so we flat map, and we return another future over here, right? So we combine these two futures together, OK? Is that clear what the code does? Yeah, OK, that's good because we'll look at it from different angles soon. OK, and I guess that's quite clear what's happening here. So what might be some potential problems with that code that we might want to improve? Because we will want to improve that code. So the main problem here is that we have committed to a very specific interpretation of side effects quite early, right? So if we look at the signature of the add points method, right, it returns a future. So when you see a future, you kind of suspect that there's something done in the background, right? But in fact, the business logic contained in this method, it has nothing to do with background computation, right? It just happens to return a future because our user repository happens to use a future, right? So the signature is kind of misleading here, right? Because we don't really need a future to express that particular business logic. It's just an implementation detail of the user repository which kind of leaked to our business logic, right? So we have committed to the specific interpretation of side effects quite early. In other words, you can say that the addPoints method is a description of a simple over here, but a description of a business problem, right, that we want to solve. And we have mixed it, so we have mixed our description of a business problem with an specific interpretation of side effects. And that's the problem that we will try to solve using either the free monads or Tagless Final. So we want to somehow separate the description of the problem from the interpretation of the side effects. And we will want to not commit to a specific container, because you can think of the future as a container for our results. So we don't want to commit to a specific container too early. Now, if you look at the code, the only thing that we really need here are flat map and unit, right? So we only really need a monad, if you know what it is. But these are the only two operations that we need from our container, right? We don't use any specific future capabilities like running things in the background, right? OK, so that's kind of why we want to actually change that code. And now we will actually try changing it. So our first approach will be using the free monad. OK? So in the free monad, the basic idea is that you represent programs as data. OK? So if you look at our business method here, it kind of expresses the business logic in terms of some simpler instructions, right? These simpler instructions come from the user repository, right? So it kind of uses these user repository methods as basic instructions to build some business logic around them, right? It finds a user, updates it, and so on. So in the free monad approach, we will write it over here. I will sit down if you allow. It will be easier to type. And I have it all written down, because otherwise I can't code without notes. So we will have a basic instruction set which will be verified as data. Okay? So we have a sealed trait user repository algebra. So don't be scared by the algebra name. Algebra really means that it's a set of operators which we are going to use to express our ideas, right? So it's really not a scary word. It just means a set of instructions, a set of operations that we are going to use. So we will express our basic instructions as a sealed family of case classes. So we will have a case class findUser for our first method. It takes a single parameter UUID. And it's an instruction in our algebra. And now the type parameter over here specifies what's the result of that instruction. So the result of executing a findUser instruction will be an option user, right? Not a future option user, because we don't really commit to a specific implementation of a side effects, and there don't really need to be any side effects involved. But if you think about what the findUser operation does, it finds a user, right? So the result here is an optional user, because the user might not exist. And the other operation will be update user, which takes a user and extends user repository algebra, returning a unit. So nothing. So no result. OK, so these are the basic operations. OK. The basic building blocks with which we will be building our programs. Now, that's yet not enough to express, to build programs like in a whole. To build programs, we need some way to express the fact that we want to have a number of sequential steps, right? Because programs, like sequential programs, they run one instruction, they take its result, run another instruction, takes its result, and based on these results, run yet another instruction, and so on. So we need to be able to express this sequentiality. And that's possible. That's what the free monad does, OK? So I'm not going to go into much detail into why the free monad is called the free monad, or like what are the specific mechanism. For our purposes, it's just a way to turn a set of basic instructions into a way to express sequential programs. And we'll see in a moment how. So we'll have the type of programs, user repository programs, a returning type A. Let's be consistent here. And it will be an alias for free user repository algebra A. Okay? Now this free, this comes from cats in our example. It's almost the same in ScalaZ, so it doesn't really matter if you use cats or ScalaZ here. It's just a helper construct. It's a family of case classes again, which allow you to express sequential programs. So we're going to use that type alias, not to type free everywhere. And that will be the type of programs which use the algebra as the basic instruction set. Okay? So this free means it's a sequential program which uses these basic instruction sets. OK, now to make writing our code a bit easier, I will define to helper method find user UUID, and it will return a program, user repository program of type option user. Now, why do I need this helper method? Is because that I could construct a single instruction, but it will live in a different world than our programs, because our programs need to be wrapped in this free construct, right? So what we need to do here is we need to return a program which runs a single instruction, OK? And that's called free.liftf, find user ID. And I'm going to do the same for the update user, user repository, unit, free.liftf, and update user audio. OK, so these are our helper methods. So they take a single instruction and lift it to return a program, which is still a data structure. It's a description of a program, or maybe more precisely. It's a description of a program which runs a single instruction. OK? So now let's refactor our addPoints method to actually use this machinery. So I'm going to copy that code and just modify it so that you can see that it's actually more or less the same program. OK. So let's begin our modifications by modifying the return type. So we aren't going to return a future, because that's a specific side effect. We're going to return a program, a description of a program, which returns an either string unit. So here we're going to return a user repository. OK? Now we don't have, we will use our helper methods, so we will just remove these prefixes here. So we are going to call the find user. That's a program which runs a single instruction. And we are going to flat map the result of that program. And if there is no user, we are going to return a pure value. So instead of a pure future value, we are going to use a pure free value, free.pure. OK. So free.pure is a program which returns a specific value, right? If you think about it, a sequential program can be two things. It can either return a value or run a series of steps, right? So free.pure returns a single value. Free.liftf runs a single instruction, and flatmap creates a sequence of two or more instructions. OK, and we are done with our, it compiles. We can even verify it with SBT. For some reason, it's very big. But it's green, so it's good. So it compiled. So so that's all the modifications in our code that we need to do to make it return a description of our program as a value. Okay? So it's not a lot. I think it's quite similar to what we had before. But when we actually run the addPoints method, nothing is going to happen, right? And it can't even happen, because we only create a description of a program in very abstract terms, right? We have no idea what find user means, right? It's just a data point. So when we actually run our addPoints method using a random UID and let's say 10, that gives us a description of a program, right? But we still need to run it at some point. So we have the description. Now we need a way to interpret the side effects. And to do that, we need to write an interpreter. Yeah, OK, thanks. So yeah, we will have a future interpreter. OK? So this interpreter will actually turn our side effects into turn our basic instructions into specific side effects in terms of futures. Okay? So to do that, we need to write an interpreter for our algebra. So now there's a squiggly arrow here. Don't be scared by it. It is you can think of it as a function between each member of the algebra and the corresponding future. Okay? It's kind of a function like a higher order function. Okay. Implement methods. So we need to apply FA match, right? So we need to return a result for every possible instruction, okay? So if our instruction is find user ID, well, here we should probably go to the database, but let's say we always return none. So that's a very simple implementation for tests. And if we update the user, I don't want to update plugins right now. It's a bad moment. So yeah, I will just return future dot successful. Yeah, one too much over here. Unit. Okay. Why is it red? Let's see if SBT thinks it's red as well. That's the. That's what you should trust, not idea. Oh, it's green, so that's good. Yeah, that happens, unfortunately, with SBT. Anyway, so that's an interpreter, right? We interpret each instruction in terms of a future. So now that has a type of user repository, right? It's a description of a program. So now we actually want to run the description of the program. We can invoke the run fold map method on it with the future interpreter. Interpreter, that's a hard word. And this will be a future either string unit. OK. So now here we have fold map. So we have a description of a program, right? And we can apply an interpreter to it, and it will automatically, because so the fold map will work if the thing that we're interpreting into is a monad, and it can actually also flat map things over there. So future, there's a monad instance in cats for it, so we can actually use fold map to run all these steps described by the program using this specific interpretation of the side effects. Okay? So what is important about our free monad solution over here is, first of all, that we have separated the description of a program from its interpretation, right? Secondly is that the program is represented as a value, right? It is a value which we can do anything. We can, so this value over here, right? We can store it in a value. We can pass it to another thread. We can use it multiple times. We can combine it with other programs. We can put it in a list and then fold the list and so on. It is an ordinary Scala value. It's a family of case. It's like a nested case classes. We can even pattern match on that and do some optimizations. Like we can take a peek what's the next step going to be and run some optimizations if we want to. So another nice thing of the free monad is that whatever the interpreter is, the free monad is going to make sure that our evaluation is stack safe, right? So we want to run into stack overflow problems. OK, so that's the free monad. Now let's take another approach, which has the fancy name of Tagless Final, but the idea is quite simple. So let me just take our original code and copy it using Tagless over here. So I said we wanted to not commit to a specific container too early, right? So let's just abstract over that container and make it a type parameter for the user repository. That's the idea of Tagless Final. So it may sound big, but it's really quite simple. So let's try doing that. So instead of returning a specific future container here, we'll just say that the user repository runs in some container f, and the operations return values wrapped in that container. Okay? It can be a future, it can be anything. It is a container, we don't know what it is, right? Now going further, we need to modify our loyalty points class over here. So now it needs to be parameterized, but by the same container f, and we need to pass that container to the user repository. So for consistency, we can call it user repository algebra, so that it corresponds. So the same concepts correspond to the same concepts. So here our algebra is no longer a family of case classes. It is a trait, right, with some methods. So yeah, so going back to loyalty points, we parameterize it using the same container. We use the algebra here. And as a consequence, the result here won't be a future. It will be an f. Right? An f of either. So it's some abstract container containing our result. So now what do we need to actually make this work? You can see that there's some red code, and even SBT won't compile it so far. So what we actually need, we can't use any container here. So to use flat map, it actually needs to be a monad. Okay? So we need a constraint here that saying that it's actually a monad, and that monad type comes again from cats. Okay? Again, you can use ScalaZ if you want to, or anything else. Okay? So we say that it's a monad, and one final change. Here, when we return a strict value, right, we can't use future successful because we need to return an f. So we need to return the unit of the monad, right? So we look up implicitly monad f dot pure. Okay, it's compiled, even in idea. So that's always nice. OK, so again, the changes were very small, right, comparing to our original code. What we have done here is that while in the free monad we have built a value that described our program, here we have built an expression, right, out of the basic building blocks, out of the algebra provided here, right? So in the free monad, you build data structures that describe the program. In the tagless final approach, you build expressions that describe the approach. Okay, so that's and here we are completely abstract from a specific interpretation of the side effects, right? Okay, so now let's write. You still need to run it somehow, right? So concept corresponding to the interpreter in the free monad, where this was like a high order function between the instruction set and future. Here, the interpreter will be an implementation of the user algebra trait. Okay, so let's write that. Future interpreter extends user output algebra. And here we are going to use a specific container type of future. Okay, going to implement the methods. Again, very simple implementations, just discarding the results. Future.successful unit. Okay, and that's our interpreter. So I guess it's a bit easier to understand maybe and to follow than the previous example. And now when we actually want to, so you know, the interpreter is just an implementation of the algebra using a specific container, right? So now when we have our description over here, the loyalty points class, and when we have our interpreter, to combine them, well, we simply run the code, right? So we can say that the result, which is a future either string unit, will be new loyalty points, new future interpreter, right? Dot add points UID random 10. Okay, and that's our result. Now the result uses a specific container, right? The description of add points over here is completely separate from the side effects, right? The only requirement we have is that f is a monad here, right? So when we look at the signature, like we know that there can't be any, unless we cheat, of course, there can't be any background operations going on here, right? if you look at the signature of the future method, of the method that returns a future, like you don't know if there's a background computation or something like that. Here, it's not possible because a monad doesn't have the capabilities to run something on another thread in the background, and so on. OK, so that's the tagless. A note here on the stack safety. So whether this evaluation will be stack safe, here it depends on the target monad. So in the case of future, it will be stack safe because future is stack safe. But in general, it's not something that's given to us by the construction. Another nice thing of the tagless final is that it has potentially less overhead in terms of allocations. Like if we go back to our example over here with the free monad, here we have allocated like a new object for every instruction, right? For every combination of steps and so on. So there are some additional object allocations. In the tagless approach, these are just expressions. These are just like code that is being run. Okay. What is important to note here is that these approaches are like equivalent in the expressive terms, so we can translate from one to the other. So there's no like difference in what you can potentially write. It's just how convenient it is for you to write it and how readable the code is. OK, so these were the simple cases. Now there are the more complicated cases when you have actually a couple of algebras, right? You rarely have a single algebra that you can express your whole program with. Right? You usually have a couple of them, and then you need to combine them into larger programs. So that's where things get a bit more complicated. So I won't write all that code, because we don't have time for that. I will just want to get you a rough feeling of how this looks like. I don't want you to understand the code, because I guess that's best done in your IDE, you know, and so on. But just to get a feeling of how this actually works. OK, so we'll complicate our example a bit. So we'll now have a set of two side effects, like two algebras. One is our user repository as before. The other is an email service which sends emails, right? It's like a separate vocabulary, separate algebra. So we're going to use these two algebras to express our business logic. The business logic is only changed over here by the fact that after updating the user with the new points, we also send an email, right? So we use a for comprehension to combine two futures together, and we return that future. Okay. So now, how do we model that in the free monad? Now it will be a bit complicated, but don't get scared. It is a bit of boilerplate, but it's quite mechanical once you get it. Okay. So as before, we have our user repository algebra expressed as a family of case classes, right? In a very similar way, we have our email algebra also expressed as a family of case classes, right? And now we want to write programs which use both of these instruction sets, right? So what we need to do is we want to say that our program uses either the user repository instructions or the email instructions, right? So we need to combine them in an either kind of construct. And that's what we do. If we scroll down over here, so we say that our combined algebra for our program will now use either the user repository one or the email one. Okay? So it's an either k. It's like of a higher level, higher order either, because it's like a either for containers, you can say, right? Because the user repository algebra is like has a type parameter, the return type, right? So that's like a higher level either. Okay? So now when writing programs saying that, you know, now I'm going to use an instruction, so it's a left user repository, a right email, and so on. So especially if the chain is larger, because you can chain more algebras like that, it would be quite tedious to write. So there's some ways to automate that and to actually inject a single instruction into a context of many combined algebras. Okay? And that's where this boilerplate over here that you can see does. Okay? So that is all quite mechanical. And as I said, I don't really want you to understand every detail of it, because that's not the purpose. Just to get a feeling. So you have to write some boilerplate when you combine languages in the free monad to combine the languages and to work with it conveniently. But once that's done, then it's much easier. Okay? So the idea here is that we have the f over here. The f represents like the final mix of our languages. So it's a chain of ithers, chaining different algebras. Okay, so that's the f in this class. And we require an implicit value that's automatically generated by cats, which says I want a way to inject my single instruction into our instruction mix. Okay? And that gives you the method, right? So for example, maybe let's go up here because we are used to the find user one. I want, as before, we had the helper method to lift the single find user instruction into a program that runs a single instruction. Similarly here, we lift the find user instruction with the mix of the languages that we are using, right? Into a program that runs a single instruction in the mix of the programs we are using. So that's the extra step that we actually need to make. You can see, well, the boilerplate for the user is like 10 lines of code, or actually 6, because of the wrapping. OK, but once we have that boilerplate, again, if we look at the implementation of our business logic, it's roughly the same as before, right? So maybe like if we had the side, it will be more apparent, but there's not much difference to the future-based version, right? So for example, this fragment over here, right, the combining of the effects of updating the user and sending an email, right, it looks exactly the same as before, right? So the business logic is expressed quite clearly. Okay, you only need some boilerplate to actually have the support for the multiple languages. Okay, so that's the free monad, where the combining requires some extra boilerplate. How is it in Tagless Final? Well, that's a bit easier. So in Tagless Final, as before, our algebras are expressed as traits. Right? These traits, again, are parameterized with the type of the container that the results are going to be wrapped in. There's one for the user repository, one for the email. So that's I guess, all quite simple. And now, again, the loyalty points implementation, right? Here it requires that we take that the container is a monad because we want to sequence our effects. Right? We take a user repository algebra, we take an email algebra, and again, the implementation is exactly the same as with the future, with some minor differences. So instead of future, here we have an f, right? Instead of future successful, we have the unit value of the monad. But again, for example, combining these two effects, right? Because f is a monad, we can just use the for comprehension just like with the future. So the business logic, again, is mostly unchanged using this approach. Okay? However, the good side is we don't need that boilerplate with combining languages as in the free monad. We just use two traits. Okay? Now, going to the interpretation side, again, we need to write. Should I finish or? Okay. Well, yeah, going to the interpretation side, it goes back. Yeah. We have implementations for both our algebras, right? So here we are using a specific type of a container that we are going to use. It's a future interpreter, right? Again, it's a simple implementations of a trait. And then when we run it, we just pass the interpreters to the class. So that's all quite simple. So in the Tagless Final, one good thing about it is that actually combining various languages, 5 minutes, OK. Combining various languages is much easier, OK? OK, so that's, I hope you get a rough feel of how combining looks like. You can then explore the code on your own. It's all on GitHub. So now to summarize what we have seen. No. Where's my slide? OK. Yeah. So just to compare, now we have like 6 kind of slides which compare free and Tagless, right? In free, if you recall, the program was represented as a data structure, right? And in Tagless, the program was an expression. So that's, I guess, the most fundamental difference between the two approaches. In free, we have built programs from constructors, which were expressed as a sealed family of case classes, and then lifted into a way to represent sequential programs using free, right? In Tagless, we have just used Scala functions for that purpose. So next in the free, the programs were plain values. Now in Tagless, a program was an expression, but what's important is that it's parameterized by the type constructor f, okay? And it cannot live, so like the plain value can live on its own. It's just a value of type free something, right? And it can live in any context. In Tagless, the expression must live in a context that's parameterized by the type parameter f, okay? And that's a bit constraining. Now, for the stack safety, free guarantees are stack safety during execution because the free monad controls the execution. In Tagless, we are just running a function on like a plain Scala function. So this really depends into what we interpret to. So if we do a lot of flat maps and we interpret into a non-stack safe monad, we can get stack overflow exceptions. Okay, that's also an important thing to bear in mind. As I said, in the free approach can have some overhead in terms of if you run a lot of these computations, it can have some overhead in terms of allocations because each operation is actually reified as an object or two objects even. In Tagless, we don't create these intermediate objects, so so it can have less overhead. In free, there's a possibility to do pattern matching via looking at the top level construct of the free monad and potentially running some optimizations or like picking ahead what's coming up next, right? So we have a potential for running optimizations. In Tagless, as I said, because these two approaches are equivalent, so we can also do kind of pattern matching, but it's much more tedious and much uglier in code. So it's not really that practical. And finally, as far as combining languages goes, in free, we combine languages using coproducts. Coproducts, that should be really either case. So Katz decided to change the name of coproducts to either K. So in free, we combine languages using eithers, right? So we just put them side by side and build a bit either out of them. And we need this inject boilerplate to actually make working with it manageable. In Tagless, that's much easier because you just have several traits that you can use, right? So you don't need all that boilerplate. OK, and finally, the question, of course, is when to use one and the other. OK, so the universal answer in IT is that it depends. But I guess some guidelines that I would use is that free might be better for some cross-cutting concerns. For example, more like library-like usage. So a good example here, I guess, is Slick. Slick has the DBIO action wrapper. When you describe some computations against a database, you get a DBIO action. And even though it's not explicitly named, it is a free monad. So I don't know if they did it by accident or not, probably not. But so they don't call it the free monad, but it is a free monad. And it is, in fact, the approach that we've been talking about here, right? And the nice thing is that it's, again, the description of operations against a database in Slick. It is a plain value. You can combine it with other descriptions, run them in a transaction, and so on. So what's nice about it is that it can live anywhere in your program, right? You can create lists of these actions and combine them together and so on very easily. You don't need that context of the resulting monad, which you need in Tagless, right? So free, I guess, is, as I said, good for like library-like usage because you have these programs as values which are very easy to manipulate. Okay? So now Tagless might be better to express high-level business concepts, maybe even using these free things. So you can mix those two. There's nothing which would stop you from doing that. So Tagless might be better for high-level business concepts and when there's a larger number of languages to combine. Right? The downside, so like the upside here is that it's very easy to combine different algebras, different core instruction sets, right? Because these are just traits. The downside is that everything needs to live in that context of the container that you are going to use in the end, right? If a library forced you to do that, that would be quite limiting, right? In your end-user business code, that's much more manageable. Okay, so do I have any more slides as 10? No. Slide n-1. So just that you know who's been talking to you, I'm a software engineer at SoftwareMill, which is a company which does custom software. In Scala, we also do big and fast data, of course, machine learning and AI, and of course, blockchain and so on. I'm personally also doing some open source projects like STTP, Macquire, ElasticMQ, QuickLens. If you are working with Scala, maybe you will find them useful. I run a blog, and I have a Twitter account, so if you'd like to ask any questions about the presentation or some of the projects, feel free to reach out to me. And slide n. No, that's again a -1. Yeah. So as I said, the material for that presentation is based on a blog that I published over here. So it covers also one more aspect of compiling into intermediate languages. If you are interested, all the code for the presentation is on GitHub. So you are free to explore if you would like, for example, to explore how you combine the languages in more detail. So that's quite easy to do. And yeah, that's it. So if you have any questions, I'd be happy to take them. Yeah.
Thank you for the presentation first. And does it make sense to mix the two?
Oh yeah, sure. So you can have So the question is it possible to mix the two? And I think yes, it is definitely possible. So you can have like a business method, maybe written in the Tagless Final approach, which returns, for example, a DBIO action from Slick. So that's entirely possible, sure. So like what you return is like completely up to you. So you can definitely mix those. So, yeah. Okay, thank you very much then again.